there is like 10 to 15 on certain indicator. And one of the science, the science application will also start for right. Just similar to what you guys are doing with sharp leads and sharp needs, but I'm trying to survey but at a high spectrum by using cross correlation, like molecular mapping, like similar message you just into that is or whatever object motion that and you cross correlate and places to see any points to see the triple loop on your GWST, recommending GWST, they also sequence.
That's it.
Yeah, BLT speaker.
And now, I know. Just and now there is
cross correlation or any specs on.
Yes. You are also in the team of iLocator.
Yes, yeah, it's hard not to be on the team. So, yeah, iLocator is mainly pushed by Jonathan Class.
Yeah.
But he needs a scientist to write papers, right? Yeah, he is very excellent. And it is actually the scientist who kind of divide, all the science case, to use it, right? And he's doing a great job in pushing it out. We already in the middle of the shooting thing where we
Okay.
And yes, I would say and it's better than home stereo. Like actually doing stuff, like it's not wrong. It's not wrong because of that. Like items will be at LBT in the spring, and then they were assembled and we can see them first. Somebody's doing that.
That's nice.
And we're already still space because instead of using shells.
Poi ho recuperato le cose, però il puntatore non ce l'ho, però qua non ce l'ho, ma faccio poi quest'altro. Ma cos'è questa? Dovrebbe connettere. Lo so, come facciamo? Non possiamo fare un hotspot. Ecco il microfono che c'ho. Martino l'ha usato l'altra volta. No, lo so. Però l'unica modo. Io non ho nessun modo di gestire il seminario al momento. L'unico modo che c'è è che lui poi alla rete. Stamattina senza il microfono esterno. Va bene, questo comunque un Mac abbastanza nuovo. Pointer ci sta. Magari quando lo presento, vedi se si sente. No, ma infatti la prima cosa voglio chiedere. Hi people, we start in a minute or two. People are still joining in. Can you hear us? Can you share some, tell us if you can hear us properly?
Yes, we can hear you.
That's perfect. Thank you.
We are working for an upgrade with an IAPS with a resolution of around, I hope, 15,000. We will have to talk with the people for this.
So, yeah. So I think I can start. welcome to the seminar organized here at IAPS Institute. It's a great pleasure for me today to introduce Professor Wang. Sorry for my pronunciation. It's 2 days and still haven't got it right. I apologize. And it's very an honor for us because Professor Wang is an associate professor at Ohio State University. He's in a sabbatic at ATC in Zurich this year. So since it's get closer, there was this possibility to invite him and have him here to present a wide panoramic of his research on exoplanets. Professor Wang got his, he started his studies at University of Science and Technology in China, but then he was very fascinated for astronomy and moved to US and to the University of Florida, where he got his thesis and PhD. He got his PhD in 2012, and then started his career on a postdoc, always working on exoplanets. He first went to Yale University in New Haven, and then moved for a 3-year postdoc in Caltech. During this period, he continued his research, focusing either on Jovian planet. Those are information I got. So if I say something wrong, please correct me later.
Cannot be wrong, because anything you say about exoplanet, I have done a little.
Yeah, exactly. And Jovian planets, and then also the recently also rocky terrestrial style planets. He focused a lot on direct imaging exoplanets in the recent year. And in 2020, he was awarded by NFS faculty for early career program. He got this award from the NSF, that is the United States National Founding System, for searching biosignature in exoplanetary atmosphere. Currently is for 1 year in Zurich, working with experts on exoplanets, and we are very happy to have you here presenting this panoramic on a college of exoplanets on the mass period diagram. Please, I ask people that are attending remotely to hold their question, to mute your microphone, hold your question till the end of the talk. We have slight problem in connection here, but we will give you the possibility to ask questions. Please write them in the chat, and we'll give you the possibility to talk at the end of the seminar. So the first is yours, Jim. Thank you very much.
Thank you, Eugenio. And have we checked the people online can hear us?
I think, yeah, I checked that
Okay.
people can hear that.
Great.
Don't go too far from the
Okay, so, okay, then I will stay around my computer.
if it's possible.
Yeah, really appreciate the opportunity to visit this institute and get a very enjoyable conversation with the people working on exoplanet, planet formation. And also, I'm glad that the people working on LBT instrumentation team coming here for this talk. So I'm going to talk to you about this topic. And I realize that the time is limited. I can only cover certain populations of exoplanets. So I combined the 2 large talk into a talk today. So hopefully I don't go over time. I'll be very mindful about that. So, see if okay, good. So for every exoplanet talk, I think it's inevitable to show this mass period or mass and semi-major axis plot. And visually you already identify different population. And also you notice that this plot is different from okay. Is from other mass semi-major axis plot, because this is done by my student. I'm teaching planetary science, and this is one of their assignment to draw all the data point of exoplanet and also plot the sensitivity of the detection techniques. It's wiggly, it cannot be totally correct, but remember they are only first year, second year undergrad student, yeah, at OSU. So when you look at this mass period diagram, you see different clumps. You also see different gaps between different population. So visually using your pattern recognition, you can see different clumps. So mass semi-major axis diagram, you can identify different population already visually. In the first part of the talk, I want to convince you that data, what the data tells you, this is what your mind tells you when you flip back and forth to identify the data point as well as the different population. And the first part, I want to also do a data intensive way to identify the different populations and how that informs the planet formation theories. So there are different populations, and from left to right, basically from hotter planet to colder planet. And at a bigger end, we have a hot Jupiter, cold Jupiter, and the directly imaged young Jupiter planet. And from bigger planet to small planet, we have Jovian planet, gas dwarfs, and the rocky planet. And you see this part of the parameter space is empty. This is not because there are no planets in this parameter space. This is purely due to the sensitivity of current detection techniques. So there are clumps and there are also gaps. What does the gaps tell you? The gaps tells you maybe there's the time scale of a certain rocky planet. When they reach a certain threshold of mass, they will quickly become gas dwarf or hot Jupiters. So this is a process that we know as a runaway gas accretion. So the gap means a very quick time scale. That's why you do not see the planet in transition from a massive rocky planet to a gaseous planet. It's like taking a selfie, right? If you're in front of a Colosseum, if you want to jump, it's very hard to capture you in the air, right? Most of the time, you either start to jump or already landing. So the gap is actually tells you that the time during the transition is very short. And also there's a gap between cold Jupiter and hot Jupiter. Maybe that tells you the different mechanism of their formation, or for example, hot Jupiter migrate into different migration mechanism than cold Jupiter and has the gap between them. So we can actually learn quite a lot or just by staring at this mass period diagram. And I will start today's journey with the rocky planet here because we are interested in habitable planets and we are interested in searching for life in the universe, and our best bet is for rocky planet. Now I would like you to take a moment to think about or envision what a habitable planet would look like. Just take the next 10 seconds to think. All right, I think from your eyes, you probably have some ideas. And so you probably think something like this. And, a habitable planet should have water, should have atmosphere, should have land for us to live. Maybe that could be an ocean world, and it's totally based on Earth. Unfortunately, current technique do not allow us to study the habitable planet in that details. We only have 3 measurables for habitable planet, rocky planet. So for example, mass, we can use radial velocity to determine the mass of a rocky planet. And we could use the transiting method to determine the size of the planet. And we could also use spectroscopy of the star or the planet to determine the chemical composition of the planet. And that's currently all the techniques that we know. And mass, radius, and the composition are the 3 observables that we could have. And we hope that these 3 observables could translate into something deeper that could help us to understand, could help us to infer the habitability of that planet, right? For example, going from those measurables, we hope to understand the thermal evolution. For example, how big the planet, how is the planet differentiated? And if the planet differentiated has an iron core, how fast does the core cool? And what is the mechanism of heat transport within that planet? Does the planet hold the magnetic field low enough to protect life on it? right? It's a lot of logical jump, just from the 3 measurables. The next few slides, it will give you some hope that is actually there are some jumps that we could make purely from the 3 observables. We can imagine this as a high school problem to build a planet from different observables. Right? First exercise is to build the planet based on composition. If we know the iron to magnesium ratio or the silicon to iron ratio, can we build a planet if we know that the planet is big enough to experience the differentiation process, right? In this case, we have to make a few assumptions, simplistic assumptions, that the planet has a pure iron core and a rocky mantle, right? That's about it. And it turns out that nature does us a favor because the iron to magnesium to silicon ratio is about 1 to 1 to 1. And if you work on the mole ratio and ask, okay, so given 1 mole of iron, we have 1 mole of magnesium and 1 mole of silicon. And we can actually calculate the structure of the planet. And the number is not that far from truth. So if you work out this core mass fraction, which tells you the mass fraction of the core of the planet, and given the mole ratio of 1 to 1 to 1, you can work out that the core mass fraction of a rocky planet is about 36%. And in comparison, 33% is the Earth core mass fraction. So this is a high school math, right? Everybody can work that out. And we could also build a planet using mass and the radius measurement. And that is more like a college physics here, because we see integral here and we see differential equation. And if we know the 3 equations above, the first one is a spherical mass, and the second one is a hydrostatic equilibrium. The third one is the equation of state for iron and the rock. You could also work out the interior structure of the planet. And to that, we know we can infer that the core mass fraction for Earth is about 33%. And in comparison, the oddball in the solar system, the Mercury, has a core mass fraction of 70%, meaning that the Mercury has a large iron core, much larger than the rest of the terrestrial planet. So it is not impossible to build a planet from the 3 observables that I just mentioned. And from these 3 observables, we can actually learn something about the planet formation process. So we already know that something must have happened to Mercury. And this is the topic I'm going to skip because it's going to take 20 or 30 minutes to go through the work. But we could actually compare the 2 core mass fractions, one inferred from the stellar composition and the other one inferred from the mass and the radius measurement to do the classification of different planets, as is illustrated in this flow chart. Starting from the top, right? From the top, we have stellar abundances. And from stellar abundances, we know the mole ratio of different elements. And we can build a planet, and we can infer its core mass fraction based on the stellar abundance. And on the right-hand side, you have mass and the radius measurement. You could also build a planet through the college physics there to get a core mass fraction from the density. And then we compare the 2, right? Mercury is actually this case because the core mass fraction based on the mass and the radius measurement is higher than the core mass fraction than inferred from the stellar abundances. So Mercury falls on this category. And vice versa, if you have the core mass fraction inferred from the density is lower than core mass fraction inferred from the stellar abundances, that means something is puffing the planet up. That means this planet is volatile rich. And in the middle, you have this boring planet like our Earth, that the core mass fractions are consistent between different measurements. And throughout the talk, I want to focus on this part, the Mercury part, because I want to tell you a very hyped concept called the supermercury, right? People have, maybe some of you have heard about Mercury-like planet or Mercury density planet detected. But our group have developed this framework in which we compare the core mass fraction as inferred from the stellar abundances. This is the purple probability distribution function. And we compare this to the core mass fraction probability distribution as inferred from the mass and the radius measurement. And then we compare the overlap part, right? The further away they separated it, the stronger evidence of a supermercury. And what we find is that a previously acclaimed supermercury K2229 is actually does not provide a very strong statistical evidence because the two distribution overlapped by a lot, and thus it is just a normal planet. But the best supermercury candidate we have so far is the Kepler 107c, because the overlap is small. That tells you that indeed the planet has a higher density, much higher density compared to what is informed by the stellar abundances. So this is just one of the few works that we have done for supermercury. So this is our best hope, which is only 2 sigma candidate for supermercury. So supermercury, we have not established any candidate over 3 sigma yet. So supermercury remains very elusive. And also our former student, Romy, who is currently a postdoc at Harvard, also developed this reputation of killing supermercuries, because we just go through all the supermercury candidate and use our framework to either support or refute the claim of a certain exoplanet being supermercury. So the takeaway from this part is that no evidence for supermercury. And if you ask, what is the implication and what is the information, how does this inform planet formation? I will explain in the next few slides. But we don't normally have very detailed data for certain exoplanets simply because small planets are very tough to measure. It's tough to get their radius, it's tough to get their mass. So the error bars is usually huge, right? You see the error bars is huge, sometimes across the chart, over the chart. But we want to ask this question, even at the individual level, we can either accept or refute a claim of certain planet being a mercury, or exomercury. Can we go from, at the population level, can we identify a population of exomercury despite that big error bar? Because visually, you could see that, right? Because this is a plot of radius versus density. This is the Earth-like planet track, or similarly on this side. And also, you see there is this population of overly dense planet floating around. So we want to ask the data, does the data support the two populations as seen or tricked by our eyes? Or, the two population is a continuous population. So for that, we have to rely on a hierarchical Bayesian analysis, try to see which model is actually preferred, right? Because in the end of the day, we just ask a simple question. Can this distribution be best described by one Gaussian, which is like my circle here, or two Gaussian, which is just two tiny circles? What does the data say? And the hierarchical Bayesian analysis, I just in a nutshell, we don't care about all those, individual planet error bars. In the end of the day, we only care about the number of Gaussians that is needed to describe the population, and also the Bayesian evidence that tells us how many populations are actually needed. So to jump to the conclusion of this study, you see that this is the mass versus the density, and this is the Earth density here, and this is mercury, supermercury here, some of the supermercury candidate there, and we ask, is single population best described the scatter or two population best describe the distribution? And the answer is actually single population give you the highest Bayesian evidence, and therefore you only need one Gaussian to describe the whole distribution. And at the population level, supermercury does not exist. So Mercury is just one type of terrestrial planet. I realize that I've kind of overly focused on Mercury, but how about super Earth and other type of planet? So this framework can be also applied to other populations to understand their differences. So I want to bring you attention to a couple of recent papers, right? The first one is by Luke and Paet. They claim there are two populations of planets around M stars. One population is a rocky planet, the other population is water world. So that is their claim. And the controversy comes from a rebuttal paper by another group, and they are saying that maybe the water world around M stars are not very well established. So what was the problem? So let's look at the data to see what the data tells us. So what the Luke and the Paet originally thought or claim is that if you look at the density distribution, so all those 20-something data points are planets around M stars, and we're looking at their density versus mass. And by eyes, you see there are population that has Earth density, and there is another population that has density that half of the Earth density. Again, by eye, maybe. But if you use our framework that I just introduced to ask how many populations, and indeed there are two populations here, right? This two population model is favored. And there is one population of rocky planets and the one population of water world. And if you ask, what is the water mass fraction? And it turns out that the water mass fraction is 78. So for this water world, the water mass fraction or volatile mass fraction is 78%. And for reference, I think Neptune has a volatile mass fraction that is about 78% or 80%. So that is what the data says, all right? But there is a caveat because, the selection of the sample can introduce a lot of bias. So this is just a very selective sample of planets around M stars. So if we throw more data points into this analysis, the evidence of the two population is decreasing. So that already tells us that sample selection is important. The other thing I want to emphasize is that maybe we should take the water mass fraction with a grain of salt, and I will explain why that is the case and why it's interesting. Water world, right? I'll bring up another controversial paper, which is the claim of biosignature on Haitian world. K218b. So it's now becomes famous because group led by Nkrumah Sudan, they find this dimethyl sulfide, right, which is thought to be a biosignature. And they say that DMS, dimethyl sulfide, is a biosignature for this water world. So is it water world or is it not a water world? Really depends on how you modeled the planet. Because again, later on, there is a rebuttal paper coming out saying that, the type of planet, what type of planet K218b is, really depends on, how you model the planet. And I'll explain that in the next slide. So here is the same population that you look at, as the previous slide. And but I swap out the model that I used and swap in a new set of model. And the only difference between the two set of model is the equation of a state of water. So previously, so the new set of model I throw in is actually having a new set or updated set of equation of state of water. And you can see that this number changes by a lot. So this is a core mass fraction of 19%. If you convert that to water mass fraction, is about 12% water mass fraction. So the same population of water world can be described by old model with 78% water mass, but by new set of model with only 12% water mass fraction. So how much water there is in this planet really depends on what kind of equation of state you use. So that's another caveat of doing this data informative analysis, which is that your model selection also, again, could change your conclusion. And also, I also want to flip back to this analysis with the old set of equation of state. You see the intrinsic scatter is very small, right? So that means maybe for this, using an old set of equation of state of water, the intrinsic scatter is tiny, meaning that this population, most of the scatter is accounted by the observational error bar, but not intrinsic scatter. So that tells you, how sharp the distribution is, intrinsic distribution. But this one, the spread is getting larger, right? That means these two populations, that could be, this population actually belongs to the distinction between the two populations is not as clear cut as before, using the new set of equation of state. So this is what we have for the data intensive analysis of planet populations for different terrestrial planet, Mercury-like planet, super Earth, and the water world, and how the analysis inform their origin of formation and their composition. So the takeaway from this part is that at the individual level and at the population level, there's no evidence for exomercury. So however much we want another Mercury in a different stellar system, they do not exist yet. And we do see a separation of water world and the rocky world, meaning that there could be a bifurcation of different composition for planet orbiting around M stars. But really, the conclusion depends on how you select the sample and what you use in the equation of state, because that will change whether or not the two populations are separated, and also, if indeed separated, how much mass there is for the water mass fraction. Then, I'm done with the rocky planet part. I will move on to the direct image part of the talk. So the whole story revolves around this poster child of directly imaged exoplanet, HR 8799. Just to give you an idea what HR 8799 is on top left here. It has 4 Jovian mass and a size planet orbiting around 8 stars that has about 2 solar masses. And all these movies are created by another Wang, which is confusing in this field, because not only we share similar initial first name and the same last name, we also share the same office at Caltech. And we publish the second author paper, Wang and Wang paper, quite often. So, we take credit for each other, basically. HR 8799, and this is Beta Pictorius B. And behind the chronograph, there is a planet C there that is recently discovered. And this is the eye of the sky, formal hot, and you see this tiny dot is moving, and it is still unclear whether or not it's moving thing is a planet or not. And this is the coldest planet ever discovered, 50 Eridani b. There are other planets that could be shown in the movie, but I picked the 4 because they kind of are representative of the directly imaged planet that we know of. Talking about this planet, we always wonder about their origin, right? Because do they form like a brown dwarf, like a stars, or do they form in a disk like a planet? So this is the question that we try to address. So actually, there are different observational signatures that we could use to help to distinguish these different scenarios. And I will explain to you a very simple two-way model. Please take that with a grain of salt because there are a lot of complications. But I think that the simple model will help you to understand why measuring the metallicity or elemental abundances of the exoplanet could help us to distinguish different formation origin. If the planet or the companion formed like a star, then they should share the same chemical composition, just like the binary stars. When we measure abundances of binary stars, most of it, I would say 99.9% of the time, they share the same chemical abundance. And here I choose carbon and oxygen because those are the element for which it's easiest to measure the abundance, elemental abundance for an exoplanet and also for a host star. So if they share the same abundances, then they form like a binary star. But if a companion forming a disk, and the disk has a more complicated chemistry, because in the disk, the temperature drops as you move away from the star. As temperature drops, one will encounter different ice lines. The closest ice line is the water ice line, right? Say if in a scenario where this planet formed just beyond the water ice line, and in the conventional wisdom of Jovian planet formation, you first form a core, and once the core reaches the critical mass, we start to accrete the gaseous envelope. Because of the location of just beyond the water ice line, the gas you accreted is deficient of water because water is no longer in the gaseous phase. So the gaseous envelope should be deficient of water. And if the envelope is deficient of water, it should be deficient of oxygen because water is the carrier of oxygen. So the data point is moving toward oxygen pool, right? The oxygen rich and oxygen pool. But the carbon abundances should remain the same because all other gases, all other carbon carriers should remain gaseous. In the system, now in the disk, not only there is a water ice line, there is also CO ice line and methane ice line and a CO2 ice line. So had the planet form at a different location, the gas it accrete will have different composition. And if the planet formed beyond the CO ice line, the gas it accrete will be deficient of not only water, but also CO because CO also condensed and no longer in the gas phase. So in that case, the planet will be, the atmosphere of the planet will not only be deficient for oxygen, but also be deficient for carbon. So the deficient of a certain element actually tells you where the planet forms. It's not as simple as that because there's also a process called core erosion and also accretion of a solid because we know that the disk is not only gas, but also the planet could accrete a planetesimal or the inflow of pebbles. And whenever the planet atmosphere accrete those solid, which is mostly made up by metals, the atmosphere is enriched. So we're going to have the different forms of enrichment, including the inward drifting dust. We'll also include the core erosion, which is actually what happened to the Jupiter itself too. Right? Over time, the core is becoming more and more diffused. If the planet is convective, and some of the metals will be elevated to the atmosphere to be observed. So the end result of core erosion or dust accretion would elevate the metallicity of that planet. So if we see an elevation of the metallicity in both carbon and oxygen, that's actually a sign of accretion. And here I just skipped about a 5 years struggle of me trying to measure the carbon and oxygen abundances, right? Because I think, you probably do not want to hear all the sad stories of me making mistakes. But I just want to share a few cautionary tales of measuring carbon and oxygen abundances as an observer and how I correct those mistakes. So the way I correct or test my method of measuring carbon and oxygen abundances and also the C2O ratio is by calibrating my method against certain accepted model, right? Phoenix model is very well used by stellar physicists and also brown dwarf people. So I want to ask this question. If I applied my method to a well-established Phoenix spectra, would I get out the same carbon and oxygen measurement, right? Because that's a good test. So because we know the ground truth and we want to test. So this is the result of the test for which I use my method again to test using Phoenix spectra as an input to see what is the measurement of carbon and the measurement of oxygen abundance, and they're right on, spot on, right? The black is the data or the input, and the distribution of blue is the posterior sample of my method. But it's not very good. I mean, it's about 1 sigma off for the C2O ratio. So that way I understand not only the statistical error, but also the systematic errors. Phoenix is just a model provided by human being, right? We also want to find some ground truths in the nature that could help us to test our method. So in that case, I use benchmark brown dwarfs. So benchmark brown dwarfs is like we know they are massive brown dwarfs, and we know the masses of them, and we know the stellar abundances of the host star. So we basically know everything about their system. And because they are massive, it's almost impossible for them to form in a disk. So the only formation pathway for them is to form like a binary star. So the benchmark brown dwarf should have the same abundances, including carbon and oxygen, as their host stars. So this is the test that we use, right? So we know the stellar abundances of the primary star, which is the data error bar here. And we can also take the high resolution spectra of the brown dwarf themselves and measure the carbon and oxygen abundances, and all of them return to be within 1 sigma of the stellar value. So that way we build the confidence of our method for our carbon and oxygen measurement, so that we're sure that whatever report is about the truth or close to the truth. So this is just to show you that what we use in our method, we use the high resolution spectroscopy of the brown dwarfs, and also we use photometry. And we basically did the black is the data and the red is the output, and pretty much all of them falls within 8 sigma, which is actually good. So we do this test not only for one benchmark brown dwarfs, but actually for quite some. In this case, I would say yes, about 8 benchmark brown dwarfs, and almost all of them falls within the stellar value, which is 0 and 0.55 within this mark, within errors. So we know that our retrieval framework, or the method that we use to measure abundances, is trustworthy. And with that, we want to revisit or tell a story of how HR 8799C forms. And why focusing on C? Because this is too faint, this is too close, right? And D is okay, but again, the separation of from the star is like 0.5 arcsecond. Also, it's still very close, and it suffer a lot of contaminations. So C is our best bet if we want to try to understand the formation origin. So the new development for us is that we have not only the archival data, but also we have this the data from KPeak. KPeak stands for Keck Planet Imager and a characterizer that gives us a high resolution data for the atmosphere of HR 8799C at a resolution about 30,000. So at a 30,000, I want to convince you that what you see is not entirely noise. And for reference, I give you the line list of CO and water. And indeed, you're going to see where you expect CO lines, there is a drop of the data point. For example, here, here, here. So we're not entirely seeing the noise due to the fact that we scattered a photon into too many wavelength channels. And another way of testing it is we use spectra, model spectra, to cross-correlate with the observed spectra and to see if we can see a cross-correlation peak, right? If we see a peak, meaning that the template spectra that we use is identical to the observation. We do that for all 4 planets, B, C, D, E, and for all different molecules, we try to detect CO, water, methane, and the combination of water and carbon monoxide. And the way to read a plot is that you find your favorite planet and you find a favorite molecule and you see if there is a peak. And if the peak, if there's a cross-correlation peak, that tells you that the water template matches with your observation. So if you measure water, you get oxygen abundances. If you measure CO, you could also get a carbon abundances. And after that, you put that into this carbon and oxygen metallicity diagram. Right, so this is a very messy plot. Unfortunately, I say unfortunately because all the data points are for the same target. All right, so this is the depressing part. This is the 5 years effort I skipped. All right, the sad story that I skipped. But this data point with a big error bar is actually what we are confident about. With a large error bar, even despite the large error bar, we know that the atmosphere of HI 8799C is enriched with respect to the standard value, which is 1, 0, and 0. It's not super significant. It's like 2 sigma. It's 2 sigma level. However, as I explained to you that not only we have measurement for C, we also have measurement for E. And later, I'm going to show you that for all the rest of the HR 8799 data, all the planet, with the exception of 1, is enriched. So that is a strong evidence that the planet atmosphere of HR 8799 planets are enriched. They must accrete during their formation process. And if we were to convert how much they accrete, so the next plot will give you an idea. So if the metallicity of the atmosphere is about 0.3 level, and then you just run a simple model to ask, okay, what is the accretion? How much solid should the planet accrete such that the atmospheric metallicity reach the 0.3, 0.4 level? And the answer is about 100 Earth masses. This mass is stunning, right? Because where in the disk can you find 100 Earth masses? If you use the solar system as an example, add up all the solid that we have, it's only 20 to 30 Earth masses. So if you want to find a huge mass reservoir, you have to trace back to the evolution of the disk. Because the earlier you go, the more massive the planet is, and the more solid it contains. So this plot basically shows you that as the planet or as the protoplanetary disk gets older, right? This is about 100,000 years. This is a million years. The number of the solid reservoir is reducing drastically. Even at age of about 1 million years, the probability of it contains 100 Earth masses solid is practically 0. So this plot, together with the amount of accretion, tells you that the planet has to form really early, before 1 million years. So that's actually a quite surprising finding from this study, which is that planet formed really early and accrete a huge amount of dust. So bear that in mind, there are a few caveats that I'm going to address. But let's go to the formation. What is the story of HR 8799C formation? So we know that C/O ratio is about the solar. So that tells us that they form outside the CO ice line where everything condensed. That's the only way to get the solar C/O ratio. And from the perspective of accreted mass, we also know that it formed very early, but it's unclear to us if they form through the disk instability or through the core accretion. Later, I'm going to show you some insight into the distinction between the two scenarios. So they form early, accrete a large amount of disk outside the CO ice line, and then they accrete huge amount of mass, but it's not through core accretion because the core can only provide up to about 10 to 20 Earth masses, because after that, the core will, the core will stop growing and the whole gas, so that the planet will enter a runaway gas accretion. So it's not through core accretion, it has to through the pebble accretion or planetesimal accretion. Then they migrate, the disk is dispersed, is getting a shrink over time, and the planet is migrating into their current locations. And we know their migration because the 4 planets are in a 1, 2, 4, 8 resonant chain. So they are migrating this. So those are the key takeaway for the formation history for HR 8799. They form early, they accrete large amount, and the accretion cannot, like the increase of metallicity in the atmosphere is not due to core erosion because it does not provide up to 100 Earth masses, and they migrate into their current location. So that's the story for one planet, right? Next, I want to move on to the story of all the directly imaged exoplanet. And then this plot is again quite stunning to me, because if you divide the companion into different masses, the low mass companion tend to have a large scattered of metallicity, whereas the larger mass or higher mass companions tend to stay around the stellar value. So this tells us that this population likely formed through binary channel, right? Like a binary star, they share the same chemical abundances or metallicity as their primary star. And this population likely formed in a more complicated environment. And we can play a same game and ask the question, for this directly imaged exoplanet, how much have they accreted? The answer is they accreted a lot, but also with a large uncertainty, right? So this is a violin plot, tells you the overall distribution of the posteriors, marginalized over a lot of uncertainties. But if you look at across the system, the average value is 53.8 Earth masses. Again, a very large value, a value that you can only find when the disk is very young. So all directly imaged exoplanets form early and accrete a large amount. So that is another key message I want to convey. So during the talk, you may have a few questions. I want to address some of the caveat in this analysis here. So caveat number 1 is that, I tell you about, the accretion is not through, like the metallicity enrichment is not likely due to the core erosion, right? It's more likely due to the inflow of pebbles or inflow of dust. But what type of dust? When we talk about dust, dust comes from different sizes. We have millimeter size dust, we have pebble that is about centimeters, and we have planetesimal that has a size of about 100 kilometers. It's unlikely to have something in between because we know that through streaming stability, dust can either come very small or very big. So when I show you the disk mass shrinking over time, that is through ALMA observation. And ALMA is only sensitive to a certain sizes, which is the millimeter size. Right? It does not mean the dust is shrinking. Maybe it means the dust grows already into planetesimals. So maybe the planet could also accrete planetesimals later on to enrich their atmosphere. So depends on really what kind of dust it accrete that could change the time scale of the formation. So we try to address that, or at least investigate into the feasibility of by accreting only inflow pebbles, a millimeter size or centimeter sized dust, can a planet form that early? So this is some of the very interesting work done by Yuxin Li, which is a 51 PAC fellow at the UC Berkeley. So his simulation addressed the feasibility of growing the planet purely from inflow of pebbles and the available solid in the disk, without any other source, such as planetesimal. So this is, let's focus on the top plot here. Top plot on the x-axis is the disk mass. So this is like 10% disk mass, 4%, 25%. Usually when we say when the disk mass is over 10%, it will enter through a self-instability and will produce a planet like a binary star system. So this is a kind of the threshold, 10%. And the x-axis is the disk dust ratio. So 1% is usually the observation, but in disk we also see regions with a high concentration of dust, sometimes can reach 5%. So what a top plot shows you that under certain disk condition that is consistent with ALMA observation, for example, less than 10% disk mass and about 5% dust to gas ratio, you could accrete, one planet could accrete up to 60 Earth masses. And in turn, it will translate into a metallicity about 0.4, which is consistent with observation of HR 8799. So at least it is feasible to grow the planet and contaminate or elevate the metallicity of the planet atmosphere purely from pebble. And someone also may wonder, there are 4 planets in the system, right? So the fact that 3 out of the 4 planets are contaminated, meaning that the outer planet do not serve as a trap for all the inflowing pebbles. So his simulation also shows that either for large dust or smaller dust, the gap carved by the Jovian planet is not entirely trapping all the planetesimals. Actually, you see through those spiral arms that will serve as a linkage between outer disk and inner disk. It is those leaky traps that help deliver the material outside to inside to feed the inner planet to enrich their atmosphere. So that is also possible in the simulation. Another caveat is that the accreted solid mass is depending on the assumption of convective envelope, right? In my calculation, I assume the convective envelope the planet is fully convective. But we know that, for example, Jupiter is not fully convective. It's only certain region is convective. If we shrink the convective mass, then the required mass of a solid accretion is correspondingly smaller. So I want to address that caveat with a recent JWST observation, which shows that I want to bring your attention to C and D here, which is the orange and the blue case. So both for C and D, they have a consistent metallicity. What I have not shown is planet B also have a similar metallicity. So all the 3 outer planets have a similar metallicity. had they have thin convection zone and accreting, for example, planetesimals, their metallicity would be more likely to be deviated from each other because thin convection zone more susceptible to the stochastic event of planetesimal accretion and therefore lead to a non-identical metallicity. So the fact that the three outer planets, B, C, and D, share similar metallicity is an indication of them having a massive convection zone and accreted a similar amount of mass to enrich their metallicity. So I think I've covered all the ground for the talk. So this is the summaries. I think for the first part, I show you a data-intensive approach to understand the different population, including mercury, which the evidence of exomercury remains elusive. And also I talk about the distinction between water world and the rocky world from a data perspective. And in the second part, I'll also tell you about the metallicity of directly imaged exoplanet and how we go from there to trace the formation history of directly imaged exoplanet. And the science takeaway from the whole talk is that, directly, at least for directly imaged exoplanet, they form very early and they accrete a large amount. And that is kind of the key message I want to convey for the part of direct image exoplanet. If I may allow, I want to show one more slide to introduce my group because I wouldn't do this wide range of research with my student and the group members in my research group. Many of them have already left the group and they have successful getting either faculty position or postdoc position. Some of them, Houston and Caprice, they recently got the Hubble Fellowship and off to Carnegie and the Santa Cruz. And last year also graduated Anusha Pai, who works not only on science, but also instrumentation. And what is shown in the mass and the period diagram are my remaining group members working on different populations. So this one is kind of has an opening here. This is because Caprice Phillips used to work on the file signature for gas dwarfs, but she left for Santa Cruz now. So I'm hoping someone will fill in that gap here so that I can still be complete for the mass period diagram. All right, with that, I will conclude today's talk and welcome any questions. Thank you.
Thank you for this very interesting talk. So we went a bit over time, but there is still time for some questions. So I will first look into the public in the audience, and then also, meanwhile, I will check online. So any question? I see. Alice.
So thanks for the amazing talks. And I have a curiosity about the population of exomercuries. You said before that sample selection can have a big impact on the kind of statistics you're able to retrieve. So do you already have an idea on how to put the sample selection?
Yeah, so sample size matters a lot. I think sample size is more critical for the distinction between water world and the rocky world. In selecting mercury, we also have certain observational bias that I have not addressed in the talk. For example, supermercury, they are more massive given the same radius. So it's easier to detect high density planet in the radial velocity survey. They also suffered the bias against them in transiting observation because for the same mass, they are smaller. So those are the observational biases that I have not addressed in constructing the sample. So, but there could be a way of addressing them. For example, doing certain Monte Carlo simulation to see how that would affect the final statistical result. Yeah, it is important, but we have not. That's a really good point.
So any additional question from the audience, Maria?
You could go back to any of those densities versus critical scale density plots on the same topic of the first part of the talk.
Go ahead.
Yeah, thank you also for this nice talk. I'm extragalactic astronomer, so what was interesting for me, I noticed with my naked eyes that, okay, yeah, it's fine. So the green points above, they have a gap and a concentration of points. But if you don't count it, they have a certain range in mass. So I was wondering why the purple points or the lower points around 0.5 line. In terms of the density, they also have a similar range in mass. So I was curious, does it make sense if you have two different populations of two different types of planets? Does it make sense that the mass range through some evolution is the same?
Yes, I think, yeah. So now we count, so not only they differ in density, they also differ in mass distribution, right? Because if you take a histogram, the mass for the water world is more concentrated around the
Yes.
4, and there seems to be a dichotomy of the rocky world. Some of them is heavily biased toward one Earth masses, some of them is larger masses. Yes, I have not thought too much about it, but again, this is the sample they used in their claim for the two density, distinct density for the planets around M stars. I'm sure with the new addition of the data point, this will be a field. I think that would be the case. I have not, so this is a work in progress as I show you here. This is so yeah, I will check if the mass remains like that there is a remain a gap in that in the mass for this population.
Does it affect the number of points because there are only 6 when you are trying to distinguish with the algorithm between two populations? Is it at least to me it seems like a small number, but I don't know your technique.
It is a small number, right? But I think the small number would also be taken into account
Okay.
in the Bayesian framework.
Okay.
And another thing is that there are new addition to this population because recently there is a Luke and Pi, they published another paper. So yeah, I have not included new data yet.
Thank you very much. It's very interesting, the technique versus the human eye, so I appreciate it.
So is there any question from people in remote, online? Can they write on the chat? I'm monitoring the chat. So I don't see any question. So I think we can talk, we can thank the speaker. Okay. And see you again for the next seminar. Cheers.